huge bulk of GCSE and A-level nuclear chemistry concerns nuclear decay. Now, nuclear decay is a type of nuclear reaction in which one nucleus, call it nucleus 1, turns into nucleus 2, usually kicking out some other kind of particle. Now, of course, we don't think of nuclei doing this, so it is limited to unstable nuclei. And such unstable nuclei are usually called radioactive. Okay, so while we're talking about nuclear decay, they're nuclear reactions, and there's more about nuclear reactions in the extension material. They're nuclear reactions, reactions of a nucleus in which it turns into another nucleus, usually kicking out a little chunk of itself as a particle. And this is only going to happen when the nucleus is radioactive, when it is an unstable nucleus. And in a later video, we'll talk about the factors that make certain nuclei stable and other nuclei unstable. Anyway, of course, the classic type of nuclear decay is so-called alpha decay. This is where one nucleus kicks out an alpha particle to make a second nucleus. What is an alpha particle, you ask? Well, I suspect you know. An alpha particle contains 2 protons and 2 neutrons, so it has a charge of 2, a mass of 4. So we will often write it as alpha, that's the type of particle, mass of 4, charge of 2. And of course, the more perceptive of you will say, well, hang on, if something's got 2 protons, isn't it something to do with the helium atom? And indeed, a lot of times you will write an alpha particle as just showing that it is a helium nucleus. Okay, doesn't have those electrons there. It is a helium nucleus. Now, of course, a little side shot here. Helium was formed, most of the helium that we have in the world today was formed by radioactive decay of particles and trapped in mines and so forth. And so we get the helium out and we throw it in balloons. We use it to make our voices squeaky. We use it because, of course, helium is lighter than air. It will float away out of the atmosphere and it's lost, which is a shame because it took billions and billions of years to make the helium that we have now, and we're running out of it. And it's extremely useful, not for making squeaky voices, but for things like MRI machines and all other kinds of issues. And so it's actually a looming societal issue that we're running out of helium. So don't use it in balloons. Don't use it to make your voices squeaky for the sake of society. Anyway, that is a helium nucleus. Now let's construct a nuclear equation showing this decay. So uranium-238, so that's an atom of uranium, which has an atomic number, a nuclear charge of 92, and a mass of 238. It undergoes alpha decay. So let's see what we got. There's 238 uranium, kicks out an alpha particle. What's left is the question. Well, we can do this not by balancing our atoms, because obviously the uranium is a different type of atom at the end of it. So when we're balancing nuclear equations, we have to think of it from 2 different perspectives, both of which are different from what we have done before, in that, again, the electrons are irrelevant, and by definition, one type of atom turns into another type of atom in a nuclear reaction. So the first thing we can do is let's just count our neutrons and our protons. We start off with 92 protons. 2 of them have gone with the alpha particle, leaving, of course, 90 behind. We start off with 146 neutrons, because 238 minus 92 is 146. We lose 2 of the neutrons in the alpha particle, leaving us with 144. Thus, we want the atom that has a nuclear charge, an atomic number of 90, and then we add the 90 and the 144 to get the mass of that particular atom. So it is 234 thorium. Look on the periodic table, 90 is thorium. Add those 2 numbers up, we get 234. There is a nice balanced equation associated with the alpha decay of 238 uranium. Now, I said that there were 2 ways to balance nuclear equations. We can indeed keep track of protons and neutrons a lot of the time, but as we're going to see in the next slide, which possibly will be the next movie, when we start talking about beta decay, you don't actually keep necessarily the protons and neutrons balanced. So the other thing that we do, and this is how we're going to balance nuclear equations for the rest of this module, is we balance the mass and the charge. So if we look at our little equation here that we generated by considering correctly, in this case, the protons and neutrons, let's look first of all at the total mass. We start with 238, and then that splits into 4 plus 234. Well, 4 plus 234 is 238. Looking at the charge now, we start with 92. On the right-hand side, 2 plus 90 is 92. So thus we have balanced our mass and charge. That is how we will be balancing nuclear equations from now on.